everyone, I'm Nada Hussein, and together with my colleagues Khadija, Farah, and Salama, we will be presenting our capstone research project entitled Unauthorized Drone Detection, Tracking, Localization, and Hunting. This project is supervised by Professor Mohammed Ghazali. Drones have been deployed in a wide spectrum of applications. Autonomous drones provide efficient alternatives for applications that might endanger people's lives or that would simply reduce the human labor required. These applications include firefighting, package delivery, agriculture applications, or even entertainment, and much more. However, unfortunately, the misuse of drones has significantly increased in the last decade. Multiple incidents were reported of drone sightings, near misses, or even collisions in airports and other privileged areas. Although anti-drone systems exist, there is an urge for a reliable, robust, and cost-effective system that is capable of detecting, tracking, localizing, and hunting down unauthorized drones.
The anti-drone systems, we have three approaches: the RF scanner approach, the acoustic approach, and the vision-based approach. In the RF scanner approach, we are detecting drones using the radio frequency, which would filter through the radio frequency of the signals to detect the drone. While in the acoustic approach, we are using a microphone array that will localize the drone based on the sound, while the vision-based approach would detect the drones using an optical sensor such as a mono or a stereo camera. Navigation, we are conducting comparisons for the different anti-drone systems that we have. We have the RF scanner, the acoustic, and vision-based. The RF scanner has the advantages of drone detection, identification, and detection beyond line of sight, as well as obstacle-free. However, the disadvantages that it has is that it's not ideal for autonomous drone detection without communication channels, as well as it requires extensive training. In the acoustic approach, it also does not require line of sight. However, no training or dataset is required, unlike the RF scanner, and it is very cost efficient. While the disadvantages of it is that it's sensitive to ambient noises, it's extremely low range detection as well as low accuracy. While the vision-based approach is miniaturized, and the disadvantages of it is that it's vulnerable to obstacles.
This is the system overview of the unauthorized anti-drone system. The system starts with having both microarrays and the pan, tilt, and zoom camera simultaneously scanning the surroundings of the plane. The microarray records the spatial audio and passes it to a sound detection network to detect the drone based on its sound signature. If a drone was detected, acoustic audio source localization is run to localize the drone in 3D. This location information is then passed to a PID controller to redirect the camera to start the vision-based detection of the drones of multiple sizes based on distance. Once a drone is detected in stereo frames, depth estimation is run and the 3D location is then passed to a vision-based tracker that continuously tracks and localizes the drones using a stereo camera. These 3D locations are then transformed into GPS-like coordinates that the defense drone uses to follow the unauthorized drone. When the unauthorized drone is within reach, either a net or radio jamming are used to hunt down the unauthorized drone.
We constructed an augmented video dataset for training and testing purposes. A drone was held on a stick and moved around in a green screen setup. The drone is moved across the frame in a way similar to how it would maneuver in real life. It gets closer, away, moves up and down, as well as turns and tilts. The background of these videos is replaced with actual footage of airport and runway videos, and the drone is placed differently, cropped and mirrored for augmentation.
For testing purposes, we combine audios of an aircraft and a drone with varying mixing ratios to produce an audio dataset that mimics the operation of flying a drone in an airport environment, since it's not possible to do so otherwise at this stage. By adjusting the amplitude of the signals, we can reduce or increase the intensity of the drone sound to simulate how close or far it is from the aircraft's position. Multiple testing scenarios were considered, including the presence of a drone in the runway. To test all scenarios, we simulate another situation where an unauthorized drone is flying close to an aircraft. Following are the experimental results we obtained.
For drone detection, a custom YOLO model was trained with 80 epochs in a 5-minute video. We evaluated the performance of the YOLO detection and we were able to minimize the loss as shown in the figures. We aim for this model to be generalized and robust to changes in scale and background. We tested our model in multiple setups and scales and variation in the number and orientation of the drones in the scene. These are samples of the successful detection of unauthorized drones. The model is able to detect multiple drones simultaneously. It's also able to detect the drone even if it's not fully shown in the frame. The output of the YOLO model is passed to a motion-based multi-object tracker. The tracker assigns a unique ID for each detected drone. These are the results of successfully tracking drones throughout the frames with the continuous uncorrupted presence of the drone in the scenes throughout.
Two types of frames are obtained from the depth camera: RGB frames and depth frames. The RGB frames are passed to a custom YOLO model for detection. This figure shows the obtained 2D location of the detected drone. The 2D location, or centroid, is then passed to the depth estimation module, which returns the 3D location of the unauthorized drone as can be. For sound detection, a mobile net architecture is trained on audios of airplanes and airport noises, as well as drones with varying volume levels. These are samples from our testing. We have set the overlap factor for all cases to be 0.3 to avoid any confusion between a drone and an airplane. In case 1, there are no UAVs in the environment, hence, the aircraft class dominates the detection with 100% confidence score. Case 2 shows a scenario when an unauthorized drone is approaching from a distance towards the aircraft, so the drone has confidence score of 30%. Case 3 represents a scenario where the drone is very close to an airplane, most probably the cockpit, and the audio model provides 87% confidence score for drone class. These figures represent the time domain representation of the audios in the mix. These figures prove that the mixed audio tests the audio model vigorously, since whenever the drone has an increase or decrease in the sound level, or when the drone goes on and off, the audio model detects the change quickly.
For acoustic localization, given the setup of the mic arrays, an audio source was placed at a known and measured location. 2 trials were conducted with different volume levels. The system successfully localized the object in both scenarios.
Throughout this project, we proposed a hybrid anti-drone system for detecting, tracking, localizing, and hunting down unauthorized drones in privileged areas such as airports. Most instances where unauthorized drones are present, illegal and threatening behavior is observed, as well as possible threats to public safety. Our proposed framework achieved reliable and promising initial results and provide a step towards a robust and cost-effective anti-drone system. That's it for our presentation. We hope you enjoyed it, and thank you.